So jumping into section 10.3. We're going to do some calculus today with our parametric equations. So the first thing we want to talk about is we want to talk about derivatives. We want to talk about the slope. We want to talk about tangent lines. So that's our first topic. So we're going to talk about we have a smooth curve. And we'll get into more details about what we mean by a smooth curve. For now, we'll just say that it's like we would expect. It doesn't have any discontinuities. It doesn't have any cusps or sharp turns, anything like that. So we have a smooth curve, and it's given by a set of parametric equations. So we have x equals some function of t, and y equals some other function of t. So we want to find the derivative. We want to find the slope of the curve. So our slope at some particular point is just like we would expect. And our slope is dy dx, which is just going to be dy dt divided by dx dt. And we're saying that dx dt is not 0. So just like we would expect, this is how we find our slope. And often you'll see this written. We can also write that dy dx is g prime over f prime, just to shorten our notation. Now, an interesting thing happens when we start taking higher derivatives. So we're going to repeat this procedure. So to find our second derivative, d squared y dx squared, we're going to find the derivative with respect to x of dy dx. And what happens there is now dy dx is my new function here. So this is going to be d dt of dy dx divided by dx dt. So notice that this is in a symmetrical situation. For each higher derivative, we're always dividing by dx dt. So our third derivative, d3y dx3, is going to be ddx of d squared y dx squared, which is going to be the derivative with respect to time of this quantity, divided by dx dt again. And we can see this by thinking of again, thinking here, for our first derivative, y is our function. So we take dy dt divided by dx dt. Here, dy dx is the function we're taking the derivative of. So we end up with the derivative with respect to time of that function divided by dx dt, and so on. We can also see this by looking at the chain rule for the derivative with respect to time. But notice that each time I take a higher derivative, I'm always dividing by dx dt. That first derivative of x with respect to t is always in my denominator. So this is kind of a interesting situation where we don't end up with a repeatedly taking derivatives for the denominator. And that's an easy mistake to make when we're dealing with parametric equations. So questions here. So really today, what we're going to be doing is using these this process for taking derivatives to find out about tangent lines to parametric equations. And some interesting things can happen with parametric equations just because they're a little different than explicit functions. All right, so let's look at an example, and then we'll talk about one of our cycloids again that we mentioned briefly on Friday. So we want to find, in this example, find dy dx and d squared y dx squared. The problem might ask us to find the slope and the concavity at a particular point. So here are our parametric equations. X equals 5 cosine t and y equals 4 sine t, and we're looking on the interval 0 less than t less than 3. And we want, at the point, 5 squared 3 over 2, comma 2. So we want the slope and the concavity, the first and second derivative at this particular point. So before we go on, thinking about what we did on Friday, what would the graph of this set of equations be? It would be an ellipse. So this is the parametric equations for an ellipse. All right, so let's find our derivative, dy dx. dy dx is just going to be dy dt divided by dx dt. And in this case, dy dt is what? 4 cosine t. Dx dt, negative 5 sine t. So I can write this as negative 4/5 cotangent t. And then we're going to find our second derivative, d squared y dx squared. And just as a reminder, this is d dt of dy dx divided by dx dt. So we need to find the derivative with respect to time of dy dx. So what's the derivative with respect to time dy dt of negative 4/5 cotangent t? 4/5 cosecant squared t. And we're dividing again by dx dt. And I can simplify this to negative 4/25 cosecant cubed t. So now we need to evaluate these at the point that they gave us. Well, this point is our x and our y, so we need to figure out what t value this corresponds to. So I'm going to say I can use either coordinate. I think the y coordinate is a little easier. So at our point, 5 square root 3 comma 2, we're saying that for sine t equals 2 or sine t equals 1/2. So what t value gives me a sine of 1/2? Pi over something. What is it? Someone said it. Pi over 6. So pi over 6 gives me a sine t of 1/2. So t equals pi over 6. I could get the same thing from my x coordinate. I would end up with cosine t equals square root of 3 over 2, and that would give me t equals pi over 6 as well. So now I can plug these in to find the values of my derivatives at this particular point. So dy dx is going to be minus 4/5 cotangent of pi over 6, which is minus 4/5. What's the cotangent, or how can we find it, of pi over 6? What is it? How do we find the cotangent of, so t is pi over 6, how do we find the cotangent of pi over 6? Cosine of pi over 6 divided by sine of pi over 6, right? So cosine of pi over 6, square root of 3 over 2, divided by 1/2, which gives me negative 4/5. Square root of 3 over 2 divided by 1/2 is just square root of 3. So there would be our slope at t equals pi over 6. And now we can find our concavity, our second derivative, b squared y dx squared equals minus 4/25 cosecant cubed. Pi over 6 equals minus 4/25 cosecant of pi over 6 is what? Not sine of pi over 6, and the sine of pi over 6 was 1/2. So 1 over 1/2 cubed, or 2 cubed, which gives me minus 32/25. So there's our slope and our concavity at t equals pi over 6 for that particular curve. And if you think about what an ellipse looks like, and just visualize the graph, it would make sense at t equals pi over 6 that our slope and our concavity is negative. We're on the upper half on the right-hand side of our ellipse. So concavity is going to be down and the slope is going to be negative. So in terms of just a way to check our work, does this answer make sense? Questions there? All right, again, be careful with this idea where when we take the repeated derivatives, we're always dividing by dx dt. We don't take higher derivatives for our denominator. That's an easy one to forget. All right, something interesting can happen with parametric equations. Since y isn't a function of x, the curves of parametric equations can cross themselves. And where they cross, they're going to have more than one tangent line. So let me grab a picture here. This is our prolate cycloid that we talked about the other day. The path of a point, we mentioned it briefly, the point on a rolling wheel takes if the point is beyond the circumference of the circle. So like the example I gave was a train wheel. So that's a path that point would take. So let me grab that picture of that. So this is a prolate cycloid. And it crosses itself here at this point. So at this point it's going to have two tangent lines. One, try to get one there, and one like so. It's going to have two tangent lines at that point. These are the parametric equations for this prolate cycloid. So it turns out that this point, 0, 2 corresponds to theta equals pi over 2, plus and minus pi over 2. And if we find the slope at this point and plug in theta equals plus and minus pi over 2, we end up with two tangent lines. Our two tangent lines turn out to be y minus 2 equals pi over 2x, and y minus 2 equals negative pi over 2x. So just something to keep in mind with parametric equations. Their graphs can cross themselves, and we end up with multiple tangent lines at a particular point. So just an interesting little fact here about these, and something to keep in mind as you work with them. If you're not sure what the graph looks like, you might want to graph it to see if you're in your calculator, to see if your answer is telling you something that actually makes sense about the curve. So this can happen with these types of equations. All right. The next thing we want to, what we're often interested in when we're dealing with slopes is, where is our tangent line horizontal? Where is our tangent line vertical? And the idea is not complicated, the method is not complicated, and intuitively it makes sense. So we have our parametric equations. X equals f of t again, and y equals g of t. So if dy dt equals 0, and the x dt is not 0, we have a horizontal tangent. And the way I visualize this is saying dy dt, so as y is not changing, but x is still changing. So y, we're not going up or down anymore. The y isn't changing, but x is still changing. That helps me visualize how it works. So that gives us a horizontal tangent line. And then I switch things around for a vertical tangent line. If the x dt equals 0 and dy dt is not 0, so I think of it, x has stopped changing, but y has not stopped changing. That gives us a vertical tangent line. So intuitively this makes sense, and we have the tools now to define horizontal and vertical tangent lines. We check for these conditions, and that tells us when we have a vertical or horizontal tangent line. end line. So questions on derivatives with parametric equations. So your problems in this section, and they'll ask you to find the slope, find the concavity, and maybe find the points of vertical and horizontal tangency. So that's really all this is doing is all we talked about in this section, all we're talking about in this section is finding these derivatives. Now what I want to do next is come up with a formula that we're going to use tomorrow, because we have quite a bit more to talk about tomorrow, and I want to come up with this formula first so that we can just jump right into talking about what we need to talk about tomorrow. So tomorrow we're going to talk about doing integrals with parametric equations. And I want to come up with our formula for arc length with parametric equations. So we're going to start, we said that if we have y equals h of x, so we have y as some function of x, and our arc length from x equals some value to x equals some other value, we said our arc length was the integral from x0 to x1 of 1 plus square root of 1 plus h prime of x squared dx. And I'm going to rewrite that as x0, integral of x0 to x1, square root of 1 plus dy dx squared dx. Now we're going to use this formula to come up with our expression for the arc length if we have our curve represented by parametric equations. So now we're going to say our curve is represented by our parametric equations. Y equals f of t, the ones we talked about before, and x. Let me switch that around. I'm going to say that's x and this is y. Doesn't really matter, but. So there are our parametric equations. And we're going to say our parameter varies a less than or equal to t less than or equal to b. So our parameter varies from a to b. And our f prime of t is greater than 0. So we're going to use our derivative in parametric form, and we're going to substitute it in here. So we're going to write that our arc length is the integral from x0 to x1 of the square root of 1 plus dy dt over dx dt, and that entire quantity squared, dx. So I'm just substituting in our expression for the derivative dy dx when we have our curve represented by parametric equations. And I'm going to say that dx, make a little substitution here, dx equals dx dt times dt. And I'm going to rewrite this expression now. I'm going to switch the page here, and we'll rewrite this expression using this, and we're going to simplify this a little bit. So my arc length is going to be the integral from a to b now, because we're going to write this in terms of t. And I'm going to, in my last expression, switch back here really quickly. In this expression, we're going to find our common denominator of dx dt squared and rewrite this radical with that common denominator. So my radical becomes dx dt squared plus dy dt squared over dx dt squared. And I'm going to bring this down to make sure we know if that's still inside the radical. And then out here I have dx dt times dt. All right, does anybody see what we can do here now? We can't go term by term here, but we have this dx dt squared in the denominator. I take the square root of that, and I have what left in the denominator? Dx dt. And out here I have a dx dt in the numerator, so those cancel. So I have s equals our arc length, integral from a to b, the square root of dx dt squared plus dy dt squared dt. And I can write that just as a shorthand. S equals the integral from a to b of the square root of f prime squared plus g prime squared dt. So this is our arc length of our curve on the interval from a to b when our curve is represented by x equals f of t and y equals g of t. Now the conditions here, the things we have to be careful of, is we don't want the curve does not intersect itself except at the endpoints. So if a to b takes us around back to the same point, that's okay. But if our curve looked like our prolate cycloid that we had there before, we couldn't find the arc length from a to b here where it crosses over itself in the middle of the interval. You'd have to do it piece by piece. So we could do from here to here, that would be okay because it's crossing over at the end point. So yeah, we would have to break it into three different integrals to find the arc length. Well, I guess we could do two if we assumed that if we were symmetrical on this side, we could just take this one and double it. But that's one thing we have to be careful of when we're finding the arc length on of these curves, that they don't intersect themselves somewhere in the middle of our region of integration, of our interval of integration. So this is the formula that we're going to, one of the formulas that we're going to be working with tomorrow. We're going to be working on finding arc lengths of parametric equations. And we're going to use arc length, just like we did before, extend that and talk about the area of a surface of revolution. When our equation, our curve is, we're going to revolve a curve given by parametric equations about various axes. So that's where we're going with this formula. We're going to use it just like we did our previous arc length formula. We're going to extend that into working with parametric equations. Okay, questions? All right. There you go.